question on the requirements for the mean value theorem. Well, for this we need two things. The first one is to actually recall the statement which goes as follows. And the second requirement is that you need to understand it. You need to get what's going on. So what does the mean value theorem tell us? Perhaps take a moment to read the statement. It says that if the function is continuous on the closed interval, as you can see here, and differentiable on the open interval, then there is a point which approximates the average for, which approximates the rate of change of the function. Now, what does this mean? So you have a function that looks like this. Yeah, so it looks something like this. Now, what it's really saying is that there is a certain line which I can draw, like this, which would approximate the. It wouldn't approximate anything. It's just a line I can draw from A to B, and this line has a slope, and the slope of this line is f of b minus f of a divided by b minus a. I think that is very clear. Now, what our theorem is telling us is that there is a certain point on this function, at which the tangent line is equal to the slope of the average slope of the function. So, first off, do you agree with me that if I take the change in f of a and then f of b, and then I divide it by b minus a, and so I take that change as well, and then that would give me the average rate of change? You should be able to agree with me on this. I hope so. I can't hear you, but I think you do. So that's the first thing I want to affirm. The second thing is there's this claim that you have the derivative at a point, which is the tangent line to this point, for example. And there's a claim that this point, you could say it averages out the derivative, which is indeed this one. And here in this case, this is a nice example, because here for our C, we have, let's say, f prime of C, and it has the same slope. It's not really placed at the same, it's not placed like this, per se, but it has the same slope. So there's a point C which has the same slope. So it's a very nice and strong result. And we've already used it to make some interesting remarks on the behaviors of different functions. And I think now we can take a good look at the choices. So f must be from a, b to r, sure. It doesn't matter what a and b are, it just matters that the interval is closed. And it needs to be continuous on the closed interval, and it needs to be differentiable on the open interval. Yes, so f must be continuous on AB, must be differentiable on AB, but I don't really see anywhere where this is mentioned. So the derivative, it can exist, but we're talking here about the derivative function, and we're asking it to be differentiable, so to be continuous. I'm sorry. And so this is a very strong claim. So what do we do here? Well, it seems that the other three choices are true, so this must be the false statement. But then let me take a look at something. Yeah. So indeed, as I was speculating, but I didn't want to say an inaccurate statement, and that is the derivative might exist at every single point, meaning that the function can be differentiable at every single point, but it does not have to be continuous. So this is a stronger claim. So not only do you want the derivative to exist at every single point, but you also want it to exist in this, let's say, very smooth, continuous matter. So this is a stronger claim. In our case, we don't really need this. We can use the weaker claim that we need f to be differentiable on the open interval. So if f is differentiable in AB, it doesn't mean that f prime, which is the derivative of f, will be continuous on AB. That's what I wanted to say. And in this case, this is now a precise statement to state.